All right, folks, welcome back. Let's get started with the topic of today, the main topic, which is backpropagation. This is the heart of neural networks, and we are going to cover that. It requires us to know, for us to understand it, a little bit of a calculus, in particular, differential calculus. Now, you may say, I've forgotten all about differential calculus. How many of you have forgotten it? Most of us. Okay. So just to give you an idea, I'll frame it as a problem. Suppose I ask you to solve this problem. Fx, let's take an example. Fx is equal to e to the minus sine x, right? Sine x to something very cute. Let's say that's square, sine square log x. Is it bad enough? I'm trying to make it as complicated as possible. Now, how many of you can immediately tell me what fx is? Derivative of derivative df dx is, which is this. You would say, well, I don't know how to do this. Would you agree? And now what I'm going to say is, and these things we go through in college, in school, we do it more as a mechanical technique. But it turns out we need a little bit of that technique today for neural networks. And I'm going to show you that this is actually a very easy problem to solve. So how is it? You don't have to learn anything fancy. But I just want you to know some very basics. Suppose I gave you a table in which I said the derivative of x to the power, let's say n, x is 1, derivative of x square is 2x, this much you remember. Derivative of sine is cosine, right? Derivative of log is 1 over x. That's what you vaguely remember, isn't it? And I claim that if you remember only this much, you can pretty much solve this problem. So how? I'd like to tell you a story, a sort of a kid's story. How many of you have, or your kids watch, a TV show called Psych? Psych? No? How many of you do? Raise your hand. Psych. How many of you liked it? So, okay, it has two characters, Sean and Gus. It's quite good, actually. If you, a whole generation of kids sort of grew up watching it. It's meant for teens, early teens, adolescents, and so forth. But watching it with my own two daughters, I got hooked to it. So I ended up watching the whole thing. Okay? So there are two characters in that. Oh, one is a very sensible, very intelligent fellow named Gus. And the other is a little bit crazy fellow named Sean. And Sean has flashes of insights in solving mysteries, solving murder mysteries, or all sorts of mysteries. But and he always manages to solve cases. It's a bit peculiar, and he's very poorly educated. Whereas Gus, is there a lag? There is possibly a lag. Okay, so in that story, Sean is a bit poorly educated and not very bright in other ways. Like he's very good with observations and practical skills. Gus is the intellectual. So one day they have to solve a mystery. Apparently, the mayor of Santa Barbara gets murdered or something to that effect. And they are supposed to find out what happened and who did it. So to do that, they suspect that one of the people standing for elections must be the one doing it. So now, how do you investigate that person? So they get the crazy idea that the only way to do that is to yourself stand for elections. So Sean goes out stands for elections, registers and says, I'm going to go for elections. But then comes the scary part. because then journalists come down, reporters come down, and they say, we have to interview you and know your position on all the important issues that matter to the citizens. He has no clue. So, for example, his answer to what is the first thing you'll do, he says, I'll remove all speed limits from the roads. So things like that, especially between my home and my house. So Gus then tells him a trick, that here's the trick. This is how politicians answer questions confidently. And that goes to the heart of what I'm going to explain to you. That brings it back. He says that whenever somebody asks you a question, don't answer that question, but you answer the adjacent question that you wished he had asked. You see the subtle difference? You answer a different question that you find easy, but it's within the same ballpark, right? And then you just go ahead and confidently answer it as though that was the question that was asked. Now, if you watch television, you know that's how politicians and a lot of executives and whatnot, people in power confidently talk and behave. So, by the way, last time, in the last batch, I told this story too. One participant raised his hand and said, Asif, now I finally know why you don't answer my questions directly. So, well, that's that. So, what we are going to do is look at this problem, and e to the x is equal to e to the x. I'll just leave it like this, a small table. What it says is, if you're given a problem, don't answer that problem. Suppose I gave you this function, fx is equal to e to the minus whatever. Suppose this whatever was z, right? So then it becomes fz. Can you take the derivative with respect to z? You can, right? You can say, well, df dz is equal to, what is it equal to? Ez itself. The problem is then, as in rebuttal, as good reporters do, they try to pin the politician back to the real problem. They'll say, well, we didn't ask you for df dz, we asked you for df dx, right? So then the next round is, okay, what can we do? The problem is, we don't know. We know z is equal to minus sine something, right? Let's mark this something as w. Now suppose z is equal to minus sine w. Can we do dz dw? And what would that be? Minus cosine wd, right? So now we have an interesting situation, but then we have an issue. We have w is equal to, what was it? X squared log x. Now, can we find dw dx? We can. This is made up of two parts, this part and this part. So we can say the 2x log x plus x squared over x log. Derivative of log x is 1 over x, isn't it? And so we come to the conclusion that this is 2x log x plus x dw dx, isn't it? And here's the fun part. So let's multiply all of these things together: df dz dz dw dw dx. It turns out that that will give you the original thing that you were seeking. So what did you do? You broke the problem down into a bite size, right? So somebody once asked, how do you eat a hippo? Answer is one bite at a time.
The left hand side is df dg, not dg dx.
Sorry. Oh, sorry. Yes. Oh, thank you for correcting me. Yes, that is certainly true. A dx. I apologize. Dx. So what we are doing is, suppose this big problem is a hippo, we are taking one bite at a time out of it, right? And then we are, well, eating it all up. And so your answer would be, therefore, e to the z is this part sorry. Then dz, this is here, minus cosine w times dw dx is this times 2x log x plus x, right? And so now we know how to solve this problem. What was z? Z was sine of this. So you will now come to e to the minus sine, what is it? X squared log x, right? Times minus cosine w. What is w? Cosine x squared log x times 2x log x plus x. Right? Did you see? Now, this is not something that could have been solved in one stroke. But if you notice it, we solved it by knowing only small bits, this little table. If you think about it, this is all the information we needed to solve this. Does that make sense? Yes.
I got lost when you said dw by dx is 2x log x plus x squared by x. Where did that x squared by x come from? I didn't get that.
Oh, what happens is that you first take the derivative. See, the way the rule is, if you have a and b, like so some function is made up of a, b, and you do df dx, it will be dA dx times b plus a times db dx. Okay, is the product rule. Is the product rule. Yeah, I should have mentioned that product rule. So now what happens is, there are two terms here. This is the a and this is the b. So first you take the derivative of a, that is 2x, x square's derivative is 2x times log x, and then the second time you leave x square alone and you take the derivative of log x, which happens to be 1 over x. You got that?
That makes sense.
Yes, good. Yeah, this is it. See, one of the interesting asymmetries of life is taking derivatives is very easy, which is why they teach you first. You know, in calculus, integral calculus was discovered before differential calculus. But they teach you derivatives first because it boosts your confidence. You can break any problem down using what we just learned is the chain rule, which I call the rule that whenever somebody gives you a hard problem, ignore that problem, solve instead the easier problem you know how to solve. Right? So, or eat the hippo bite by bite. So that's your chain rule. And it turns out that integral of every function is not known. In fact, integration is so hard that just about every function that can be integrated, most mathematicians know. Right? And the vast majority of functions cannot be integrated. Okay. I mean, you can compute its value numerically, but you can't express it in a closed form. So that's a bit of a tangent. So how is that relevant to backpropagation? I will show you what it means. See, suppose you have a neuron here. Remember, what was a neuron? It was made up of a linear piece. And let's take a one-dimensional input. Let's make life easy. X is the input. The temperature on the beach is the input. Right? The entrepreneur has to figure out how much ice cream will you sell on the beach, right, on that particular day, given that temperature. So what happens here? You get Z, do we remember? And here, they think of it, there's some weight attached to it, some amount of, the way I look at it is a variable resistance, W, that you can change. And then you attach a baseline term. So your first equation is Z, I will call it Z1, is equal to W1 X plus B. Would you agree? B1. So far looks good, guys. Right? So this is what Z is, isn't it? A linear combination. And then we know that we use it and then do what? Distort it. We put an activation function. Why do we need an activation function? Otherwise, you won't get the universal approximator behavior at all. Right? A chain of linear functions, linear transformations is still linear, but much of the world is non-linear. Right? So we do that, and so we get, let's just say, sigma of Z1. Activation of Z1 is the output. But then, as far as the second neuron is concerned, this neuron is concerned, it doesn't know that it is getting output from another neuron. All it sees is this is the input for it, isn't it? So it has its own weight sitting here, a bit of resistor sitting here. Think of it like that. So you have a network in which there are two rheostats kind of thing, things that you can change the resistance of. So here there you have a Z2 and a bias term B2. So what will be the value here? Z2 is equal to W2 times the input going to this. What is the input going to be? Sigma Z1 plus B2. And what is this network, neural network? This chain of just two simple neurons. What is it producing? This is your output, right? This is your prediction, Y hat, isn't it? That will be, Y hat will be sigma of Z2 because the activation is sitting here. So far, so good, guys? Right. Now, what happens? Your machine says, hey, you're going to sell 53 pounds of ice cream. But on that day, you actually sell only 50 pounds of ice cream. So you have a discrepancy, isn't it? You have an error. That error we'll write as a loss function, right? Loss function is a function of Y and Y hat. It is basically the discrepancy between the ground truth and prediction from your machine. Does that make sense, guys? And if your prediction is not quite right, what does it mean? Oh, goodness, let's go and turn the knobs, adjust the knobs so that it makes better predictions. You need to do that. But you need an efficient way to adjust the knob. You have to know which way to turn the dials, which way to turn the knobs, which way to move the resistors. Are we together? So how do we do that? And we learned about that trick. We say, all right, very easy. For each resistor, so this is what we want. We say W1, we change it to, let me just put a tilde here to say, we update it to this value is whatever W1 was, the previous value, minus what? Some learning rate, some tiny step, because we take tiny steps, times the loss, the gradient of the loss with respect to W1. Do we remember that? It is simply the gradient of the loss with respect to W1, gradient. Likewise, we know that this is our update rule, minus alpha, oh, sorry, W2. So this we know. The only problem is, this is called the gradient. This is called the derivative. Is the gradient descent part.
And the W1 is the
W1 is the weight here, right? So this one is here, is the resistance here. And this one is the resistance here. So we need to adjust a little bit both of them, right?
Oh, for the second.
Yeah, because we know that we made a mistake. We got it off by 3 pounds. So we need to turn, so to get the prediction right, isn't it? So what we need to do is we need to have some rule to update it. And the rule we learned is that this is how we'll update it. We need to compute the derivative of the loss with respect to W2 and W1. But you notice that L is not a function, it's a very indirect function of W2. It's a function of Y hat, right? Y hat is sigmoid of Z2. Z2 is a function of W2, right?
Yes.
So that looks like, let's eat the hippo bite by bite. Make sense? Right? So we do that. Let's do that. What we do is, we say, see, what we want is, we need this derivative. Let's take this derivative. W2. What do we really know how to do? We know that, let me take this example. Suppose the loss, we write it as Y hat as Y minus Y hat square. Right? I'm deliberately skipping the summation. In reality, it will be summed over all the training data and all of that. But let's skip all those things. Let's think intuitively. This. So we know that we can do this. This we know how to do, isn't it? That we can compute as minus y minus y hat. Something like this, isn't it? I'm skipping the summation and so on and so forth, being sloppy about summation. Because let's just focus on the main idea. So in other words, I can compute that. That one is easy. So let's start with that.
Is 2 into y minus y.
Oh, that's right. That's right. 2 also. Might as well. Thank you for correcting me. I'm being even more sloppy. So see, I come from theoretical physics edition. I think I mentioned that. But there, like, if you ask what's the relationship between mass and energy, the famous equation people write as E is equal to mc squared. Right? But if you then that's what I learned in college. That's what I learned in high school. Then I joined graduate school to do research in theoretical physics, quantum physics. And I noticed that nobody writes this. What they write it as E is equal to m. What happened to C? They said, well, just assume that the speed of light is 1. Right? Something like that. Right? It just simplifies. But if you think about it, when you write it like this, the intuition is obvious. The intuition is energy and mass are the same thing. Right? Isn't it? So in the same way, like, even though you're summing over so many points, please forgive my sloppiness when I say, forget about the summation in there. It just adds clutter. So we know how to compute this part. Let me say y hat. In reality, there'll be summations and so on and so forth, but they'll just clutter up the equation. Do that. Well, you can say that's lovely, but which is the same as, this is the same as sigma, because this is what it is, right? Sigma z2. But it doesn't solve your problem. Now you have the problem of sigma, right? So what you need to do is, you will probably do, what is the derivative of sigma z2 with respect to z2? That you can compute. Why? Because let's say that sigma z2 is equal to I'll take an example. 1 plus e to the minus z2. Something like this. This is the sigmoid activation function. It's a function. Then you say, okay, what is its derivative with respect to z2? d sigma d z2. What is it? It turns out this is well known. We know what it is. It will be nothing but sigma 1 minus sigma. You can convince yourself that's what it will be. Okay? So we know this part, we know this part, and now what remains? dz2 dw2, partial derivative of z with w2. Now, do we know how to do that part? Of course we know, because we know that z2 was, what was it? Weight 2 times, what was it? Weight 2 times
B.
Z1 plus B2, right? So we can easily compute Z2, W2 is equal to sigma Z1, right? So now we know this also, right? And so we say, so I can do this part. Do you see that, guys? This part I can compute from the chain rule. Lovely. So let's celebrate that, and we are going to no, Z2 is not a constant. Z2 is W2 times sigma. Oh, B2 is a constant. Bias is always. Yes. And so you could do, see, remember, I'm doing with respect to W2. Yeah. But when I was doing, and that's a very good point, if I was doing B2, what would it look? Because even the bias has to be learned. So in close analogy, it would be almost the same, sigma Z2 sigma Z2, d Z2, and then what would you do? D Z2 with respect to d B2, isn't it? This is what you would do. And then it would be just one. You see how simple it is? So both the weight and the bias you can update, right? So let's celebrate. We know how to do this part. So now let's look back at this equation. This blue thing says we know how to update W. W2 can now go to W2 tilde. We succeeded at updating it. Yay. But what about W1? That is a little bit more journey to go, isn't it? What we are trying to do is compute this with this. So let's start our journey there also. But by now, you pretty much have a hint of how to go about doing it. By the way, guys, the intuition is this. You know, it's a like this. Have you ever seen this? I don't know, the best way the intuition that I have is these are real functions. You know, you do something, it has a consequence. That has a consequence. That has a consequence, right? So if I made a little change here, what will be the eventual consequence? That's what your chain rule, that's what you're getting from all of this. Function of function of function of something, right? That's the real deal here. Now that we have become smart at this, let's do this. W1. That's what we are trying to do. Or likewise, DL, DB1. These two things we have to compute, right? Let's play a game. We know how to do this part. This part we can bring it down, right? DL, D sigma Z2, D sigma Z2, D Z2, D. Now, what was Z2? Z2, D Z2, with respect to what? D sigma Z1, right? D sigma Z1 with respect to DZ1 times DZ1 times DW1. There we go. We know how to do this. Right? So think about it. What is happening? You compute this gradient. Once you are able to compute the gradient with respect to this, that you need, because see, that you need, because that's what it is here. That is what you need to compute the further gradients. So first you have to compute the gradient. Like once you get the loss, so think about the journey. You fed in X. Let's take the forward journey. You fed in X. X went through this, and produced this, right? Y hat. Then out of Y hat, you got, compare it to the ground truth, you got the loss. From the loss, you got, and now we start the backward journey. You got gradient of the loss. From the gradient of the loss, you computed gradient of the loss with respect to W2, right? And from there, from there onwards, you started computing all the way, the grade, you propagated all the way now to finally gradient of the loss with respect to W1, right? You could not have computed this before computing the second one, right? That is why you say that the gradients flow backwards. You take a large neural network, loss gets computed, it leads to the first layer. So now generalize from this idea, guys. I made a network which had only one neuron there. In reality, what will happen? The real networks look scary. There are lots and lots of neurons interconnected. That's why if you notice, I use partial derivative symbol, right? Because each thing is responding to the effect of many weights. It's not a, but I made it as a single linear problem so we could do direct derivatives. But the idea remains the same, right? This entire thing that we just did, this is back propagation. Propagation of what? error gradients.
So this is for one training data in
No, one mini batch. So
mini batch.
that's why I ate up. See, remember that. So now let's get formalized. Well, I was cheating because I wanted to give you guys the main idea. In reality, you realize that this is all summations here, right? The summation over all the points in the mini batch, right? But see, if I put it in, then the whole equation becomes cluttered. If you look at your textbooks, right, it won't be, it won't look so neat. It will look very messy with lots of summations and lots of arrows going here and there and so forth. I try to simplify it down to you by taking a very simple linear circuit. See, anything that is simple, you can always complicate it slowly. Let's get the main idea. So it's my way of saying, let's first understand this and then bring in other
So
things.
you used only 2 points. Huh? You used only 2 points here. Two neurons. Basically.
Then you can keep going back. So now you have a chain, and now each layer, I have only one neuron per layer. You can throw in lots and lots of neurons.
So the sorry, my thought, like, so this backpropagation happens after the batch is done.
Yeah.
Then the error rate is
Computed.
computed. Then
Yeah. So let me explain that. So in reality, what happens is, now let's get to real life. This will have lots and lots of neurons. You will send in a mini batch of data. Right? Mini batch of data. It will go to the next layer, right, which will be very complicated. In reality, what will happen is every neuron will send its firings to every neuron in the second layer. So when you draw it out, it begins to look pretty complicated. Do you notice that? If I actually draw all of them out, it begins to look horrendously complicated. Well, I don't know if it is even worth drawing out anymore because it begins to look really messy. But this is what is happening. There we go. Right. And then it goes to the next layer and the next layer. And finally, in the final layer, you have a prediction, right? Which will produce your, yes, go ahead.
Oh, I was curious. I noticed for the bottom two, you didn't draw connections to the top neuron of the second layer. Is that on purpose or is that just...
No, it's just there.
Okay.
Everything is connected to everything.
Cool. Just double checking.
Yeah. And then the same thing happens here. It's just a big mess, like very complicated. And then you end up producing a y hat. Right? And there are many, many layers that are there, but the y hat that you get, you produce the y hat of all of them. Loss is made up of the errors between y minus y hat for each of the points, let's say squared. In this particular case, if you take some squared loss, right? This is your net loss over I. And so gradient of the loss is with respect to all of them. This is your net loss, whose gradient you find.
Going to the second class, the double descent, the error, what if it happen if it reaches the double, the error is...
No, double descent is a completely different phenomenon. Don't mix it up.
Oh,
Yeah, don't mix it. That's at this moment, just assume that this is how machines learn.
So, how would when you're computing this on the GPU, how do you think about it in terms of parallel computing? So every calculation goes to every core.
Yeah, of course. So what happens is that, and this is where, see, if you look at this, every neuron is computing its own Z, it's computing its own activation. This operation is massively parallelizable at each layer.
So is it like for every core, every GPU core, it's calculating for one neuron?
Yeah, or these GPU cores are pretty smart. You can, they internally have parallelism. So each core may be going through 5-10 neurons at the same time and computing it as a matrix. So these ultimately become matrix computations and matrix activations. That's why it's all about handling matrices. Go ahead.
So, last class you showed a kind of a demo where you can add the networks nodes and one we have a N2, N3, N4.
Yes.
But in reality, the models, they themselves will add more networks if the losses.
No. You have to decide. You have to decide. You have
How
to.
many networks?
You know, this is the process of learning. How does the network learn from data? Right? The backpropagation. See, you remember, wait, 1 second, guys. See, let's go through the 2 steps. Every neuron, see, think about it. This neuron is sitting somewhere in there in the network. It is getting lots of inputs, W1, W2, W3, right? And it has its own bias term. Right? It doesn't care. It is one of the billions of neurons in the network, potentially. What does it really care? It says that I need to update these 4 quantities. So B tilde has to go to the previous value of B minus B, right? Or whatever. And W1 of that particular layer, right, has to go to W1 minus DL, the W1.
That's what I was asking. It's part of the backpropagation.
Yeah.
So for at each neuron level, we find the tilde of
Yes,
They-
every single, very good
bias.
question. Yes. So what happens is first you compute the gradients.
Right.
And then, so here's the thing, guys. What does backpropagation do? Now, everybody knows the gradients. So every neuron can take a step of learning. That's why it's the step, right? And so it does a gradient descent step, right? And you literally call this, you say gradient, all the gradients get computed. Then in the code, the next line you say step, then they will all take a gradient descent step because they can now, because the gradients is computed. So they would all have updated their weights. Are we together? Right. So that's how it is. Go ahead.
Just to double check my understanding. So a gradient can only be computed layer per layer. So the layer beforehand has to be done.
Then
And then-
before the next layer.
And then the weights are adjusted, and then the next layer. is
No,
done.
no, no. You don't adjust the weight. So first, what you do is you let
Oh,
all
so-
the gradients propagate back,
And then
you encode. In practice, you say, okay, all of you learn now. Take one step of learning, and they all do one step of gradient descent at that particular moment. Right? Cool. That's that. Right? And you will see that in code. In a little bit, we'll see the code happen that way.
So in terms of institution, mapping to that ice cream example. So there was a prediction made that so many ice creams were gonna be sold.
53 pounds of ice cream, let's say.
This is fuel sold.
Yeah.
Plastic delta, and then I was going backwards and then correcting.
All the knobs are turning. The step gradient descent will turn all the knobs a little bit, improve them, so that if you were to give the same batch of data, the prediction will be better now. It won't be 53. Let's say 50 was the ground truth. It might now predict this time around. So what happens is you don't learn completely. You take a tiny step of learning. So maybe it will become 52.5 pounds. Right? And then, so you deliberately want to learn in very tiny steps.
So what if the answer is yes or no? It can't be really.
Oh, then your loss function is different. We'll come to the classification loss function. But you can do that. So then what happens is, machines never produce yes, no. Yes, no is your interpretation. They produce a probability, a number between 0 and 1. If the number is greater than half, you say yes. If it is less than half. So what it will do is, let's say that you're shown a cat, and the machine initially says probability of cat is 0.2. It's not a cat. Right? It's a dog. Probability of dog is 0.8. Now it needs to learn. So the next step, it will say probability of cat is 0.3. Right? It made a little bit of an improvement. So remember, guys, that these neural networks, at the end of the day, are what? They're giant functions. They're very complicated architectures, but at the end of the day, they are just effects. Right? Vector functions. Yes.
Just a follow-up to that, then, so the network is learning by itself, and the data input is remaining the same, is going backwards and then relearning.
Yeah.
And then is recalculating, so, and what it eventually is doing is all by itself, without any changes in the external data. At what point does it stop learning?
It's your choice. So what you do is, think of it this way, and that's what I now want to bring in that terminology. Imagine your data is a heap of sand, right? What you do is you take a shovel, right? And the amount that you take a mini batch of data. Think of it as a shovel full of data, right? And you feed it to your neural network. So what you send in is one byte of data, one batch. It's called, the word that you use is mini batch. That data, as it makes its way, you'll get a prediction out of it, right? Or rather predictions, prediction one. For all the little data points that are there in that mini batch, you'll get predictions. Losses will be there. This machine will learn. Then you'll go and get another batch of data, another batch of data, another batch of data. And soon this sand pile will be done, right? Every
Backpropagation happening while every batch is being.
Yes. So for every batch of data, you have the forward journey, loss computations, loss gradient computation through backpropagation, and a step forward. 4 things happen. Let me write them. For every mini batch of data, for every mini batch of data, you do 4 things. Forward pass. What is that? That is just FX, isn't it? Number 2, that becomes your Y hat. Loss computation. Whatever your loss formula is, compare it to the ground truth. Are we together, guys? Right? What's the next step that we do? Compute all the gradients by backpropagation. Propagation, right? And what is the 4th step? The real learning step. Because if all the gradients are computed, learn by one gradient descent step. And then what do? You're done with that batch of data. And then you go and pick up your shovel and get another batch of data.
You have to update the weight and bias.
Yeah, the learning part, the gradient descent step updates the weights and bias. That's exactly what the gradient descent step is. Are we together? Yeah.
What do you mean by just one gradient descent step? Is that
Means gradient descent step is this that we talked about. Huh?
okay? Okay, so
this
just the
This is the step, gradient descent step. But this is what we talked about last time, isn't it? This is the step of learning. The heart of learning in machine learning is this. Guys, I know this is all very new, but is it sinking in? Is it making sense? Right, it is, I hope. Right? So, by the way, backpropagation is perhaps, and today is probably the last of mathematics. If you're getting worried that, oh God, every time I see Asif, it gets more mathematical. Right? It doesn't get any more mathematical than this. Today is the end of it. Today is the end of foundations, guys. Huh? On this now, it will become regular computer science from here onwards. We'll build different neural architects. So what happens is, now we learn.
I have a question.
Go ahead.
On the last, after doing all that like 4 step, right? After the back propagation and the learning step. So with that mini batch of data, right?
Yes.
Will do that, take the same data and do that same forward pass again in order to see that, okay, what the result would be, or
no. You go to the next mini batch of data.
okay.
So what you do, and this is the part I want to emphasize, guys. So what will happen is, gradually as you take bite and bite and bites of mini batches out of it, you would have visited every piece of the data. Isn't it? You would have emptied the pile. But imagine that as a mini batch of data is fully visited, you put it up in another pile. Right? You're storing it in another pile. That this is the data I've already used. So it's making this journey through the neural net. Are we together? Now what happens is, when you have visited all the data points once, you have finished, and that's a concept that's important. You have finished one epoch. Epoch is one whole journey through all the data, all the training data. Are we together, guys? But then nothing prevents you from starting all over again. A good practice is shuffle the data up so that it's not the same mini batch, right? So just with sand, right? Just go mix it up, make another pile, and then start scooping from it.
What do we do with this result? So after doing the one step, what do we do with the result? Because after completing the step 4,
Yeah,
we
it's
have
a
some
good point.
white.
I'm coming to it, guys. I'm coming to it, guys. So, guys.
After one question.
Uh-huh.
So going through one epoch doesn't guarantee that a learning curve is flattened, right?
No, it does not. And that's the main point. So guys, let's look at that. What is happening as epoch after epoch of data is going through? What do you want? You want to reach a state of minimal loss, isn't it? When minimal loss means when your predictions closely match the ground truth. Mm-hmm. Loss is a measure of how divergent are your predictions from the ground truth. Are we together, guys? Loss is a measure of how much divergence there is between ground truth and predictions. So obviously, as you go through each step of learning, what should you like to see? That the loss is going like flattening out, right? It is saturating till you can't learn from it. Now, what may happen is, as you keep going through steps, 1 epoch, 2 epoch, at some point, let us say this is epoch, let's say this is epoch 1. This is somewhere here. This is epoch 2. And these are the steps in between, mini batch steps in between of learning, right? Epoch 3. At some point, you would agree that, okay, by epoch 4, you're done. There's no more learning to be done. Would you agree? Right? So that is when you say, okay, now I stop. Make sense?
Asif, so each epoch is the entire heap of data randomized.
Yeah, visited once.
Randomized with mini batch, and
Yes.
then we reshuffle it again. We
Yeah.
re-randomize it and rebuild the same mini batches, epoch number 2, and keep repeating it until the data combinations have been used and the learning happens to the flatten of the loss.
Absolutely. So guys, the physical intuition you should have is, see, think of the data as a heap of sand. One epoch is when your network, your machine has learned from every grain of sand. That is one epoch. Does that make sense? Now, you take shovel full of sand, makes a mini batch, you feed it into the network, but ultimately it is computing its loss over that shovelful, over that mini batch. Then it asks for the next shovel, the next mini batch, the next mini batch, the next mini batch. And soon you have visited every grain of sand in the heap. You finished one epoch, but it doesn't mean that you can't start over. There is more learning to be done. From the same grain of sand, you can learn many times. And so you shuffle that heap of sand and you repeat the process all over again. Each time you visit through all grains of sand to learn, it is one epoch. Does the vocabulary make sense, guys? Right? And so what are you doing? You have, if you look at it from a coding perspective, you may decide on a certain number of epochs that I'm going to train it. Let's say my intuition says 5 epochs should be enough. Or you realize that your cloud bill is going through the roof. You can afford only 5 epochs, right? So you decide that. So for epoch 1 to 5, what do? You get mini batches for each mini batch. For each mini batch, you do the 4 steps. What are the 4 steps? 1, forward, fx, y hat is fx. Now, do you guys remember what was the second step?
Loss.
Compute loss. Compute loss, L, y hat, right? For example, for regression, it could be y hat square. For classification, it could be different. Whatever it is, whatever your loss formula is, right? You could do that. 3. Now what?
Backpropagation.
Yeah, backprop and compute all gradients. And now that all the gradients are known, what can we do? We can take a step of gradient descent learning. Step of gradient. This is the learning in machine learning. This is the heart of it, this step, right? And this is step of gradient descent updates all weights and biases. Isn't it? All weights and biases. So this is the inner core of a double for loop. Does that make sense, guys? Yeah. It is the inner core of a double for loop that you are locked in. Albert.
So what about if there is another, you've not reached a minimum?
Well, then you cry over it because you said, okay, if my program has terminated and the learning has not stopped, what can I do? Well, actually, it's not that bad. What happens is, so long as you remember to store the model state, you can load it up and then do the fifth. Let's say that you ran through 5 epochs, right? 1 to 5. And your loss curve hasn't flattened, hasn't saturated. What can you do then? Load the model back up, run a few more epochs. Right? But why would you start with a small number? Because you're raking up a bill in the cloud. Right? But if you have local hardware and you have the time, then you can be more relaxed. You say, okay, let me run it for 50 epochs. Guys, please mute yourselves. So
if that happens, we should increase the gradient descent, the values.
The learning rate.
The learning, yeah.
The learning rate.
No,
not the learning rate. You can play with it.
It converges faster, right?
You could do that, but the trouble is, remember what happens when you take giant steps. You may miss the minima altogether.
Yeah.
So that brings us practical reality. See, learning rate, you call it the hyperparameter of the model. How many epochs practically is determined by the data and the problem, right? So what people do is, after a few epochs, just freeze it. Like say, I'm going to run 10 epochs, but then I'll save the model. If it has not been fully trained, I can always reload the model and start where I left off. Run for another 10 epochs. But let's not run it for 1,000 epochs unnecessarily, especially if I'm dealing with something like 100 million data points. Makes it? Yeah.
Can the step 3 and 4 can be together, or what does it need to be?
No, you don't do it. Like theoretically, see, this is a question I think somebody else asked, that the moment I find for a given layer, I find its gradient, why not do the gradient descent right then and then go to the next layer? Or for computational reasons, you don't do it. In a clean way, you do all the gradients and then you do all the steps. Yeah. And you'll see it in PyTorch, right? This whole literally becomes optimizer dots, backward and then step.
So you need to remember the gradient changes for all the new.
That is right, and it remembers. Okay. One of the nice things about this, that is why PyTorch is and TensorFlow and this JAX and TinyGrad, etc. They're auto gradient frameworks. So what happens in reality is, I say that they are very clever at computing gradients as soon as they can. Right? So look at this. They will compute partial results. The moment a function goes out there, they will know at least one part of the derivative, namely local derivative. Right? They don't know the derivative. Yeah, 1 second, please. They don't know the derivative with respect to the loss which is going to come, but they know the derivative with respect to the output they just produced of the function. Yes, please go ahead.
So on the inner loop, okay.
Yes.
First mini batch I ran with the set of data, and I've calculated the weights and biases at the end, fourth step.
Yes.
So then I'm going for the second batch inside the inner loop.
Yeah.
So at that time, the new whatever that the previous learning, the weights and biases, I will change that one, right?
Yeah,
for
so
the
the
input.
weight shifts, yeah. So at every step of learning, each mini batch improves the weights and biases a little bit. And the next batch of learning improves it a little bit further, right?
Okay. Yeah.
So it's slowly learning, the weights and biases are drifting towards the right value. So one way to look at it is, if you look at it in the space, let's say that the only weight and bias is this is the weight, this is the bias. Let's take just one simple example of weight and bias. Let's say that the optimal value is here. And you start from some random value of weight and bias. So this is your optimal value, W star, B star, right? What will happen is you will start making a journey, not a straight journey, but a journey. Your values will start drifting with each mini batch, with each step. You will start making small journeys, small steps in more or less the right direction. Why did I make it zigzag? Because a mini batch would have errors, right? Like there's also noise in the data. But you hope that when you run through many, many steps, those errors keep canceling out. And you drift in the right direction.
So I have two questions. How many epochs do you need to determine that you have hit the minimum?
You don't know. You keep looking at this graph. You keep looking at this graph.
No, but okay, at some point the values will start stabilizing.
Yeah, that is it. Till it stabilizes. So, like I said, in this particular case, four epochs are more than enough. Yeah. So every problem and every network, these are empirical evidence. There is no theoretical basis to know a priori what the correct answer is. You do it, and then empirically it emerges.
And my second question is, you said you can checkpoint and save the model and get back to it.
Yeah.
What exactly are you saving?
Oh, all the weights and biases. So, see, saving a model is more or less synonymous to saying, I know the neural architecture. All I need to know is what are the weights and biases. They're just floating point numbers, and you save it to a file. So these days, you download these ginormous models. You hear that, oh, Llama 2 has come out, or Zephyr, or this or that, GPT-2, GPT-3. All of these have come out. When you download it and you poke into the file, people are saying, what the hell? It just seems to be a giant mess of numbers. All there are matrices because they are the weights and biases.
Elon Musk called them .csv file.
Yeah, go ahead, Pawan.
So conceptually or intuitively, you could use something like this to project the sales of a company or prediction of a stock price in future.
Yes. So now let's look at the implication of it. We know how to train a neuron. Now, what is it? Remember, what did I say? This machine is a universal approximator. If you believe that the output is responding to some force of the input, unknown force, unknown function of the input, right? Which is, you have to believe that, right? If input is truly a predictor of the output, then there is some forcing function between the input and the output, right? You may not get to this, but you will end up discovering y hat some function g through this neural network where g is a very close approximation of that unknown f. So the only question that you have to ask is the problem solvable? It is solvable in a way. Well, there are certain problems that are hard to solve, but basically, in principle at least, it is solvable through this process, so long as you can be sure there is a function that relates the input to the output. Any problem that you can formulate in this way, in principle, there is hope that you can train a neural network to it. Right? So it applies to stocks, it applies to predictions, it applies to weather, it applies to think about what you want. Right? In fact, it's very close to the whole causality itself. Right? If there's a causal relationship between X and Y, then Y has to be some function of X. Right? Generally.
Asif?
So
who are currently using this,
Guys, 1 second, remote, wait, let me finish it. Go ahead. Go ahead.
do we know any companies who are currently using this to make like stock market predictions or other predictions?
Wall Street uses neural networks extensively. We live in the world of algorithmic trading. Yeah. All right. Zoom. I think I stopped.
Asif, I had a question. Asif, so in all this, what is the role of the learning rate? Does it happen per layer or is it for the entire?
No, you set the learning rate
as
for one step in one journey of a mini batch through the system. You keep the learning rate fixed. So this is a very good question that I got asked. Let me put it this way. I deliberately didn't bring up the learning rate because learning rate is a whole topic. It's called the learning rate scheduler. It asks this question that, see, I wrote this equation as W tilde is W minus alpha gradient of, let me just write it in vector notation, gradient of the loss, right? Implicitly, I said the learning rate is fixed for this simple situation. But now it turns out that that's not a very good idea because in the beginning, remember what did I say? That you can miss the minima if you go too fast. But then when you're here, there is no reason to inch your way down. You can take your learning rate, can change at different parts of the journey. Right? So in reality, what happens is the learning rate itself is a function of the steps, is another function. Let me just call it a S function of which step you are in. Right? In this loop, I'm in the 4th step of the 5th mini batch, 100th mini batch. So learning rate in a more dynamic situation, in reality, itself is a function of how far in the journey of learning you are. That's a very good question, and great that you asked.
So the learning rate adjustment or adaptation is built into PyTorch?
Oh yes, of course. If you don't give it, it will fix it. But generally, and this topic is usually considered a slightly advanced. I'll introduce it at some point. Learning rate scheduler. If you look into PyTorch under this topic, you will see a whole family of powerful learning rate schedulers. Right? So, for example, one learning rate scheduling would be that based on step I, the learning rate alpha may go down like this. It's a linear decay learning rate, isn't it? It could be an exponential decay learning rate like this, right? And so on and so forth. There are many. So this is linear decay learning rate scheduler. This is exponential decay learning rate scheduler. Right? So there are many different learning rates. And of course, there is the constant learning rate. Constant learning rate, which is the simplest, you don't do anything. Mahesh, does that answer your question?
Yes, it does, Asif. Thank you so much.
Yeah. So there are, see guys, I'm giving you the big outline, right? The main framework, the big ideas. But as we move forward through all this, you will realize that there are many subtleties along the way. Like I wrote it as a gradient descent step. Actually, it's called the optimization. The word for this is the optimization step. What you call gradient descent step, optimization step. It turns out you don't actually do it just using this formula. There is more to it. There is momentum-based gradient descent. And in practice, you use a momentum-based gradient descent. So let me give you a little bit of an intuition. See, what happens if you have a situation like this? You realize that here the gradient vanishes and you can get trapped in a local minima and you may think the problem is solved, right? So how do you avoid a local minima? The intuition comes from physics. Imagine that you are a rolling ball and the ball has certain amount of momentum. What will the ball do? It will climb over the hill, overshoot, And therefore, it will happily continue its journey to the real minimum. Right? So that brings in the concept of momentum. And that is actually the topic of next week. Right? Optimizers, the topic of next week is optimizers. Optimizers. But it's a small topic, and it would be the last of the theoretical topics. I will introduce it, but now is the time for us to learn some real neural architecture. So what I will do, how much time is it? Is it time?
So Asif, can I ask one question, Asif?
Go ahead.
So you mentioned f of x and g of x as functions. So will we ever know what the g of x is going to be? Or is it
No,
going to
you
be
learn G. No, this was the unknown, this is the hidden reality. Because hidden function or real function. See, when you have data, some real function produced it, right? You'll never find that out. All you will do is you will find G, which is a very good approximation to F. Remember, we said in the lab.
Yeah, that G, we find it, because there's a neural network going to find it for us, or we need to assume that, oh, it's going to be like a polynomial function or something like that, and then fine tune it with.
No. You will never know. Actually, it's never so simple as a Poisson function or anything. It will be some reality, and the neural network won't tell you what it found.
Oh.
It will say, I'm making predictions. Be happy with that. Right? Right? So that's why neural networks are black boxes. That's why they are black boxes. And you have to just say, it found some G that is good. It's a universal approximator, function approximator. It found a G. I'm happy with the G. I'm happy with the prediction. Now let's live with that.
Okay, so that's what you said is a model with all this learning rate biases. It has kind of numbers. That's your model, basically.
That is right. That's your. 1 second. I'll come to you also. Go ahead.
Yeah. So let us assume we have trained the model and it is predicting properly and the loss functions.
Yes.
Now, let us assume that there is a weather report that the model has been trained to come up with a weather report.
Yeah.
Now, there are many other influences outside which will tamper this weather. Right? So, can the model take the real-time input of all these configurable data or the influencing factors and then do the prediction based on the union?
Okay, so I'll repeat the question for those of you who are remote, and correct me if I got your question right. See, let's say that you build a weather model, and the weather model takes in certain factors, right? Input. So let's say that it took input, temperature, I'll make it real for you, temperature, pressure, wind speed, and historical facts, like because weather models are autoregressive. They make predictions on what has been happening in the last few days. History, let me just call it history, to simplify the autoregressive nature of these models. And let's say I put in humidity, so forth, right? These things they go into your neural net. You will feed in all of these things, the current values that you're observing and the historic things that are there, all of that data, and out will come a prediction. So now your question is, it is also missing out on some other factors that may be there. Right? For example, there may be a tornado forming in the next, or a hurricane forming in the next 150 miles away, and that's coming your way. So the answer to that is, see, if you make a model only out of these parameters, then it will always make the parameters that it has seen and learned to make predictions from, never from things it has not seen. Which is why weather modeling is hard. And what people do, these models that people make for weather prediction, first of all, weather prediction is usually not one model. The United States weather prediction model machine has more than 1,000 models, because weather is one of the most complicated physical phenomena. Atmospheric science is a whole science devoted to it. And there are 1,000 and more models that go into it. And those models, each of those models see almost all the factors that you can imagine. So for example, if there's a tornado forming or a hurricane forming anywhere, there are models that will factor that in and make prediction. Right? And generally, everything that you can imagine that can affect the weather, you feed into the model. Right? And so, but having said that, come again?
So, let us assume that there is no other additional external
Yeah.
elements to it.
Yeah.
Only with this.
Yeah.
The model is trained now for the current 4 days or 5 days, you could feed in a different value for these.
Yes,
and
every
then-
time, moment to moment. So what happens is once the model is trained, so what happens, guys, we are still looking at the training phase. Once you have run through all the epochs and you're happy, you freeze the model. Right? You say, I have a frozen model. That's the word people use in our field. And you say it is ready for inference. It's ready to make predictions. Then you just bring whatever the new data is happening, whatever the new reality is happening, you keep feeding it in, it will keep making predictions. Are we good? There? Yes.
So in the same line, right? If it is a huge variation, right? We have to train the model, or
very good.
The
So
can handle some of
yeah. I will answer this question, but let me repeat it. So when question from the audience is, suppose the model, we notice that the predictions from the model that the scientists trained and gave to us is not quite working. Its prediction and reality are divergent. Right? Then what do we do? Well, you take this data and you go back and train another version of the model. Remember, the model is frozen. One copy is being used for inference. That doesn't prevent you from taking another copy of the model and continue to train with the new observations. So that's how you do model update. So generally what happens is a model is an inference and another copy of the model is learning from the new, the divergence between the predictions it's making and the new reality. It's continually learning. Right? And you keep doing it, otherwise your model will drift away from reality. And these days you notice that. See, weather prediction has been very interesting. I remember when I was young, there used to be a cartoonist called R.K. Lakshman, I believe that was his name. He used to make lovely prediction. One of his prediction was that one person sees that on a bright sunny day, somebody is roaming around with an umbrella and immediately identifies, must be the weatherman. Right? So weather predictions were notoriously bad. And then NASA and all the satellites up there and all the atmospheric sciences advanced. And weather predictions became very good. Very, very good. Even today, they can tell you that there's going to be rain and blah, blah, blah. But recently what's been happening is climatic, like long-term weather prediction has again become poor. Can you guess why? Because atmospheric phenomenon has become highly unstable because of global warming. So all the old models have begun to not work so well. And they are being retrained. But the thing is, it's the world is changing so fast that models are having tough time catching up and learning. Right? We're in a very unstable world. I'll answer your question. I'll take the questions in a break. I'll just, this is a great moment, if you will humor me, for me to bring in a saying, which is there, I believe, in China. It says, the worst curse you can give to somebody is to say, may you live in interesting times. And the other part of that curse is, may all your wishes come true. Because interesting times are times of war and trouble, right? Good times are when nothing happens. It's boring. So anyway, I'll take a break. Krishnan, your question.
Yeah, on the weather, I don't know whether you told or someone. So Google has, now has a service where they can predict the weather just from the past records.
Yeah.
Okay.
No, whether all of the data, all the learning is from past records.
No, unlike the weather prediction happening, that is looking at all the variables coming from sensors, right?
Yeah.
That's what traditional weather prediction is about. But these guys are just using the historical records.
Yeah. I have to look into it. One more thing so I'll look into that, Google. I'm not aware of that. I do know that Facebook has created, and these days it's becoming very, our simulation ability is becoming so good. There's a huge thrust to create the so-called digital twins. And one of the demonstrations you have is you see the whole earth and the weather, and you have a digital twin, and people are trying to see how closely they can. When the weather is somewhat stable, it's a pretty close digital twin. Right? So a lot of people are getting into that with AI. All right, guys, should we take a 5 minutes break and then I still haven't answered yet.
One question is, so you have all these temperature, pressure and all that,
Yeah.
right? What if I feed in something that is totally orthogonal? Like
You can't
stock
feed in.
Let's say while draining it,
Huh.
I pass in stock price as one of the dimensions, right? It is totally unrelated to the other data and it's not related to weather, but I just feed in the stock price.
It will learn to ignore it.
It will learn to ignore it?
Yes. So yeah, this is a very good question from the audience. One person said that, what happens if you feed in something orthogonal and irrelevant into the models? It is called feature importance, the term, there's a technical term for it. And one of the good things that neural networks are, something that neural networks are pretty smart at, is that when you feed it a lot of parameters, lots of input variables or features, it actually does what is called dimensionality reduction, right? It knows which dimensions to just ignore.
So how does it know that it is not here somewhere in the point somewhere it's designed?
Yeah. So what happens is, see what happens. So let's say that the reality was made up of just x1, x2, x3, and you give it a function which goes all the way to x10, and these are irrelevant factors. So what it will do is, you may feed it, but when you look at the function that it actually builds internally, it will just ignore all the irrelevant ones, and it would have created a function effectively something that is a lower dimensional function of only 3 variables.
So basically, it will randomize away the bad data. So
yeah, it will
won't make an
marginalize it
effect
away.
on the.
Yeah, that is right. It
Okay.
does it automatize, and that's one of the virtues of this. Yeah. So see, it is a robust. It goes to robustness in models. In machine learning models, it's a vast landscape of lots and lots of models. For a model to be able to know what matters and what doesn't matter is one of the most crucial learning that it has to do, and it knows how to do it.
But it could be possible that it can be little relevant to the bias value, right?
What do you mean by bias value?
So some value trying to accommodate, right? Like this is the range you can, the bias you can try to avoid, right? For the,
I don't follow.
Like ice cream, the example, like school, why suddenly the data is increased because of holiday on that day? Because of the, I think it's bias.
Oh yeah, you mean the unknowns, the factors that are unknowns. Yeah, see,
how do you differentiate between bias versus the bad data?
See, so there are 2 factors to it. When the machine cannot learn from your data because there's bias errors in a statistical sense, a bias variance sense, it means that your network is not sophisticated enough. Make a bigger network, right? That is one reason. The second aspect is, if the data itself has a systemic bias, realize it is learning from the training data. Whatever you give, it will learn from that. Right? So I'll give you an example of systemic bias in the data. Let's say that human temperature is a perturbation around 98 degrees Fahrenheit. But you give it all the data with a +5 bias. It turns out that temperature, the normal temperature is now 103. What will the machine do? It will always predict with the +5 bias. There is no way the machine can know that there is a bias in the data. Isn't it? That's how it goes. Yeah.
So is it anything to do with the guardrails, whether you add this in the guardrails or the
Oh no, guardrails is a completely different world. That's a world of LLMs. Forget that. Yeah. We are learning foundational stuff at this moment, like what is a neuron, how does it learn, and so forth. Yeah. So we are worlds apart. See, you're bringing in things from the boot camp, which is
so basically that's the restricts, right? The guardrails is one restrict.
Yeah. So that is at the level of massive networks. We are dealing with the foundational theory. We are not yet there.
So just ignore it.
No, there's no way to put guardrails. You're putting in input out, input in, input out. Right? Numbers in, numbers out. Yeah. Remember, guardrails are texts which somehow get converted to numbers, etc. We are still keeping it simple. X in, Y hat out.
So Asif, like I didn't get your comment on bias versus number of layers of neurons. How does that get related?
No, see what it means is, first of all, let me distinguish because there's bias and bias and bias. There are 3 it's become a homonym. There are three different bias words, meanings to bias. One is, guys, when we talk of the weights and biases, weight, a bias, right? Treat bias as just another parameter. It's a learnable parameter, right? That is it. That is bias, one meaning of bias. Meaning one of bias. The meaning two of bias, completely different, is meaning two of bias is the statistical bias. Statistical bias errors. It is of the word is bias errors. Bias errors happen when your model is too simple. G that you learn is too simple. It doesn't capture the complexity of the real world, the data, right? So an example is that suppose your data is like this. And you build a model that is like this. This purple model sort of works, but what is its main problem? It doesn't capture the complexity of the data or the underlying function. It would have been far better if it had made a model like this, isn't it? So the purple one compared to the green one suffers from bias errors. That's the second meaning of the word bias. The third meaning that people brought up is what if, and the one that I used just now, what if the data itself has a shifted, like, you took a thermometer, right, which made +5 degrees or some, has a systemic bias, right? And by the way, those of you who have a mechanical calibration of the weighing machine, after a little while, you don't lose weight. What do? You quietly bend down and add a little bias error, -5, right? And then you feel good. Okay, I lost some weight. So that is a systemic bias in the data, right? Meaning 3. Of measurement. This is the
data distribution.
Yeah, of the measurement equipment itself. Is the calibration bias. Right? So the word bias, and of course, the fourth meaning of bias is the social bias, which at this moment, please don't bring it here because we are not at that level, right? So
in neural network, which one we are referring?
Oh, depending on the context, all of these are. See, this is a neuron, so of course it has the meaning 1 of bias. If you make your network too simple, not enough neurons. So this answers the question about layers. Not enough layers, not enough neurons in the layers. Then you will have the second kind of bias. And if your data itself has been mismeasured, then you will have the third kind of bias, which of course the network cannot cure.
Yeah.
Right? Yeah. That's that.
So roughly speaking, your number of layers corresponds to something like in traditional machine learning terms, like the polynomial increase of
that is right. Very much. That's a very good analogy, Gopal, that you gave. Think of layers as adding flexibility, adding polynomials, if you were thinking polynomial regression, higher degree terms. That's one good intuition to carry.
Yes,
Thank you.
I know you're going to weight will be updated. Bias also will be updated using the gradient.
Yeah, of course. See, this word use of bias is rather unfortunate because ultimately weights and biases are the same thing. They are all parameters in the model, right? They all learn by gradient descent. Right? They all, whether it's a weight or bias, the tilde value is weight or bias minus alpha this. Doesn't matter whether it was the weight or the bias, right? That's it. Any questions, guys? So with that, let's take a small break and then I will take you into the practical PyTorch. 5 minutes break, guys.
So, yeah.